Hello, and welcome to today's lecture on the scientific origin story. I'm your professor, Dr. Rob Steffen, and today we're going to talk about what astrophysicists and cosmologists think happened in the earliest days of our universe. Now, we tend to associate terms like origin story with religion and mythology, but science has its own story to tell, and it too has changed much since the early days of looking at the universe. So let's take a look at that tale as it stands today.
If you've ever had any fascination with outer space, you probably know the name Hubble. The Hubble telescope, of course, is one of the most powerful ever created, and it allows us to peer not just across the vast expanse of our universe, but also literally back through time. Because the speed of light is not infinite, when we look at light from far distant galaxies, we can be looking at them as they were hundreds, or thousands, or even millions of years ago.
So, usually we know Hubble as the guy associated with the telescope. But in terms of the scientific origin story, what's really important is the motion of the galaxies and the implications of that motion on the origins of the universe.
Working at the Mount Wilson Observatory in Pasadena, Edwin Hubble was interested in the movement of galaxies. And even though other galaxies were immensely far away, we can track whether they're getting closer to us or farther from us using the Doppler effect.
So you probably know the Doppler effect, of course, in a sound sense, right? Think of a train coming towards you as it goes from that deep rumbling to a high-pitched sound when it's close to you, going back to a deep rumbling in the distance.
Hubble realized that this same principle could be applied to the movement of galaxies. And not only that, but if we could get a sense for how galaxies were moving, we might get a better sense for how the universe as a whole worked. What Hubble discovered was mind-bogglingly unexpected. Every galaxy was moving away from us. And not only that, every galaxy was also moving away from every other galaxy.
So what we're looking at here is known as a redshift, and this is the visual equivalent of that train that's getting deeper in pitch as it's moving further away. So instead, with galaxies, as they move further away, their kind of light along the spectrum becomes more and more red. Now, when we look at kind of the expansion of all the galaxies, it makes you think, how does this actually work? And the best analogy here is think of a balloon, right? And if you put dots all over a balloon, right? A deflated balloon, they're going to seem very close to each other. And as you inflate that balloon, all the dots are not only going to get further away from you, they're going to get further away from every other dot as well.
So why is this such an important discovery? Well, let's just think of this process in reverse. If everything is moving away from everything else, then the universe is expanding. And that means that the universe is bigger today than it was yesterday, and bigger yesterday than the day before. Take that idea to its logical conclusion, and you eventually end up with a point. What astrophysicists call a singularity.
So now we need to think of that balloon deflating, right? All of those galaxies, all those points on the balloon are coming closer and closer and closer together. And once it gets to that point, the singularity, we're talking about something with near infinite density, something way smaller than any given atom, and something incredibly, incredibly hot, hotter than the core of the hottest sun in the universe today.
Now, most cosmologists, that is, scientists who studied the origin of the universe, agree upon this idea of the singularity. By tracking the rate of expansion, they've been able to date the beginning of this expansion, likely around 13.7 billion years ago. Moreover, scientists feel confident with how things progressed just microseconds after the expansion began, down to 1,000th of a thousandth of a second.
And for all the things that we can explain, there are many things that we can't, right? We can't explain why the Big Bang occurred. We can't explain the moment itself. And we can't explain what happened before it. It's simply in those very, very small fractions of a second afterwards, that's where our understanding begins.
The moment of violent expansion that erupted from the singularity is what we call the Big Bang. And in the earliest fraction of a second after the Big Bang, matter and energy mixed together in an immensely hot, soupy mass. Believe it or not, we believe things were moving faster than the speed of light, something never again to occur after this first fraction of a second. And as a result, we call this period of rapid expansion the inflationary period.
So things in the beginning really were chaotic, right? So maybe the Greeks, who believed chaos to be the earliest divinity, didn't have it that wrong at all.
During this earliest phase, we get the creation of tiny particles, protons and neutrons and electrons, the building blocks of matter. But it's not until nearly 400,000 years later that these eventually coalesce into the universe's first atoms. Stars came even later, more than 200 million years after the Big Bang. So about 13.5 billion years ago, once the universe had cooled and slowed down enough for gravity to be able to hold larger clumps of matter together.
So it's during this very early period that the conditions of life are really set. So we get the four major forces, we get the speed of light set during this period, but everything's moving around so quickly that it takes much, much longer for matter to kind of form and then aggregate into larger structures.
With this process of expansion, the universe continued to cool, allowing for matter to clump together. Protons and neutrons clump into atomic nuclei. Atoms clump into stars, and stars clump into galaxies. And within these cores of stars, things are so hot that many of the heavier, complex elements are created. All of these structures, stars, planets, galaxies, go through life cycles of birth, life, and death.
So we have stars of all shapes and sizes. And the biggest stars, when they're dying, first they expand, and then they collapse in on themselves, and they get so dense that eventually they explode, spewing matter and energy throughout the universe.
This explosive death of a giant star is what we call a supernova. And they're essential to the perpetuation of new stars in the galaxy. In fact, our star, the Sun, and its surrounding planets are thought to be the product of just such an explosion. Speaking of our planet, the Earth is about 4.5 billion years old, about a third of the age of the entire universe. In the earliest days, the Earth would have been a rather nasty place to live. There was no oxygen. Carbon dioxide and sulfur permeated the atmosphere, and volcanoes would have been erupting constantly. And this is happening as the Earth is constantly bombarded by asteroids, meteors, and other interplanetary debris. Somewhat amazingly, within a relatively short amount of time, life arose, about 3.7 billion years ago, less than a billion years after the planet was formed.
Now, the earliest forms of life, dating back to 3.7 billion years ago, well, that wasn't much life at all. We're really talking minuscule things. And it's not until about 500 million years ago, with something we know as the Cambrian explosion, where we get the diversity of life that we see in the world today. So think of 500 million years ago as kind of the starting point for really complex life forms that we'd recognize in things like our ocean today.
Humans don't enter the picture for much, much longer. Our pre-human ancestors start walking upright about 4 million years ago. Perhaps surprisingly, the use of stone tools predates genetically modern humans as well, going back as far as 2.5 million years. That's like 2 million years before modern humans. Genetically and anatomically modern humans, technically called Homo sapiens sapiens, only arise about 200,000 years ago.
So what that means is that we've only been around for 1,000th of 1% of the life of the universe. And for 190,000 years, out of the 200,000 years that people have been around, we've basically done the same things. We wander around looking for food and trying to eat enough to stay alive.
It's only about 10,000 years ago that people eventually settle down, start farming, domesticate animals, and live in one place. And then it's only about 5,000 years ago, 3000 BC, that truly complex civilizations arise, with diverse cities and monumental architecture and social hierarchies and technologies like writing.
So while we're a relative latecomer to the universe as a whole, we've been able to do quite a lot in a very short period of time, especially the last 5,000 years since civilization has gotten far more complex. So what are the takeaway points here? Well, one, we're just a very, very small piece of universal history. But in that very short period of time, we've come a very long way, at least compared to our evolutionary ancestors. And the evolution of our brains, the complexities in terms of language and thought, that allows us to tell origin stories of our own, the type that we get in ancient Greece, Egypt, and the Near East. So just a few takeaways from
the scientific origin story.